Today we're going to be talking about acid-base reactions. So I'll be introducing the concept of an acid and a concept of a base. I'm sure people watching have like a vague idea of what an acid is, just by like colloquial use. You know, there's citric acid in sodas. There's citric acid in fruits. There's acetic acid in some sodas. I think it's Sprite has acetic acid in it. And you know, acids have that sour taste. Um, Sour candies have citric acid, powdered citric acid on them to make them sour. So in the base, people might have less of a vague idea about that because it's less colloquially used. But you know, something bitter like soap. Soap is a base. Soap is the the cookie cutter example. But I'm going to be talking about something a little precursor. So a lot of AP Chem classes don't go really deep into these concepts, and I think that's a shame. Because this concept is so important for organic chemistry. If you don't know acid base, you're screwed in organic chemistry. You're going to spend so much more work learning acid base, so you can learn the organic chemistry. And on top of that, the organic chemistry is already hard. You know, if you haven't heard the stories of organic chemistry, it's kind of the killer for pre-med students because it's required for pre-med for some reason. Well, I do know the reason, but that's not important getting into. So I'm gonna write this down. Very important for organic chemistry, and that's typically abbreviated as OChem. And you might be thinking, why would I need organic chemistry? Pretty much anything, even vaguely related to the life sciences, needs chemistry or organic chemistry. Almost obviously, when you're listing off some majors that require it, we have chemistry. This is just coming off the top of my head, so I might miss some. Chemical engineering, environmental engineering, we also have, let's see, biology. It's required for biology majors. Biochemistry, biochem, genetics. It's also very important for genetics. There's also biomedical engineering, or yeah, I'll just say bioengineering. Bioengineering. And in some cases, it may be required for biophysics, if that's even offered at a school. That's what my major is biophysics. Well, it's not my major is physics, but that's beside the point. So it's either strongly recommended for that or going to be straight up required. So there's a lot of disciplines here where it's required, and then pre-med's not a discipline, but it's also required for pre-med. So if you haven't heard before, you can go to med school with any major. It's just pre-med has certain requirements. You take 2 semesters of biology, 2 semesters of general chemistry, 2 semesters of organic chemistry. Maybe physics is required. I'm not sure. Stats, sociology, anatomy and physiology. So it's required for pre-med. You could be like a math major and go into pre-med. I know some people like that, but it's required. So pay attention. And that's why I'm going to be talking things from a fundamental level instead of just like on the AP exam, you'd see like acid plus base does this. You don't really understand it. So I'm going to go there. So the first idea is defining a Bronsted-Lowry definition. And there were 2 guys. Bronsted, who was Danish. Bronsted. That O with the cross in it is a letter in the Danish alphabet. So Bronsted and Lowry, they both developed this definition in theory, independently of each other, but at the same time. So they both got the credit for it. So Lowry was English, Bronsted was Danish, and the basic idea is that here's how an acid is defined. We have hydrogen attached to some anion, reacting with another random chemical. These A and Bs aren't specific chemicals, they're just placeholders. And they react with, I'll explain the double arrow later, to form HB, HB plus. So the hydrogen goes to the element B, and the anion gets liberated almost. And what's defined here is this is defined as the acid, and this is defined as the base. So when an acid and a base react with each other, what happens is the acid donates a hydrogen to the base, and the base takes it in. That hydrogen is also just a proton. Um, so you'll hear acid sometimes called proton donators and base called proton acceptors. So more or less, or a less abstract example, let's see, on my paper here would be water reacting with ammonia. So we have water plus ammonia. And I chose water very specifically here. And this reacts and forms hydroxide, OH minus, plus ammonium, plus NH4. NH4 plus. The idea here is that what's defined as an acid and what's defined as a base. Oh wait, you just have two people join the stream. Hey guys. So we just started working on the acid-base material. I was just talking about why this concept is important. So what's defined as an acid and what's defined as a base here is whatever is donating the proton and accepting the proton. And I hope here you can see the water. It'll help better if I write the water like this. This is an H bonded to an OH. I hope it's a little intuitive to see that the water donated the proton and the water donated the proton and the NH3 accepted it. So the water here acts as an acid and the ammonia acts as a base. And I use water here for a particular reason. We typically think of water as being neutral, and at 25 degrees Celsius, it is. It's exactly neutral. It has a pH of 7. And pH of 7 means neutral. So the water itself is an acidic. It just acts as an acid. So the water itself is neutral, but it can act as an acid, which is kind of weird. And the other example I can give you here is HCl, hydrochloric acid, which the name gives away that it'll sort of act like an acid, but you can't always make that generalization. We'll see that later. Hydrochloric acid plus water forms hydronium plus chloride. And we can see here that the water this time acts as a base. Hydrochloric acid, unsurprisingly, acts like an acid. And there's a specific term for this. This means water is amphoteric. I'll make that distinction there. This means that water is amphoteric. Amphoteric. And this essentially says that given a general Bronsted-Lowry acid-base reaction, water can act as either the base or the acid, which is nice. So I'm going to draw this reaction up here too, just to make things a little more physically obvious. So we have water, which the Lewis structure for water is an oxygen, 2 hydrogens, and 2 lone pairs in the oxygen. So this molecule is bent, but more bent than something with only 1 lone pair because those electrons are repelling the bonding pairs. Plus an H3. And what an H3 looks like is a lone pair on a nitrogen. And on the nitrogen, there's 3 hydrogens. Actually, I'm going to draw the proton that's donated in a different color to make things a little more obvious. So that's a hydrogen. 2 lone pairs plus NH3. So we have that, and this reaction forms OH minus, which looks like this with 3 lone pairs now. And this has an overall negative charge plus, and now that hydrogen comes back here, the hydrogen that was donated. NH3. And then this overall has a positive charge. So there's neat things we could look at here. We can look at the stoichiometry. On this side, there's 1 oxygen, 1 nitrogen. Let's see, how many hydrogens? 1, 2, 3, 4, 5. 5 hydrogens. And on this side, again, there's only 1 oxygen. There's 1 nitrogen, again. And again, 5 hydrogens. And if we look at the total charge of the reaction, the first one, the water is neutral here, has a charge of 0. So the total charge, this just means sum of all the charges. Q is charged. That funky looking E says add them up. So sum of the charges is 0 for the water, 0 for the ammonia. So that's water. We'll abbreviate that AMM, ammonia. And over here, this equals 0, by the way. I'd hope you know that. The hydroxide has a charge of -1, and then the ammonium has a charge of +1, and that equals 0. So everything works out here. And that's the example. The hydrogen gets ripped off the hydroxide, or the water, forming hydroxide, and that hydrogen gets attached to the ammonia, forming ammonium. So the next thing is conjugate pairs. And basically this says, well, what about the HB here? This forms something else. This is a conjugate base, I think. No, it's a conjugate acid. So the HB there is a conjugate acid. Conjugate acid. So conjugate is, looking at the term, conjugate is a very commonly used term in the sciences. Conjugate just basically means something paired together. Like if you had, I guess, if you had like 2 dogs, one could be your conjugate dog. Sorry, but then you're playing favoritism for your dogs, and they don't deserve that because all dogs are great. So that's conjugate acid, and the reason why it's an acid is because if you think about it, the HB plus, a neutral charge can be sort of seen as an equilibrium, and the HB will readily give away the HB. I forgot to mention the double arrow. The double arrow means that reaction is happening in reverse at the same time. And this is a conjugate base. And I'm going to denote that with like a probability notation. A C in the subscript means conjugate. And it's almost easier seen if I write out the reaction in the other direction. The other reaction in the other direction is here. We'll do this. In the other direction, it's HB plus A minus in equilibrium with HA plus B. And from here, you can clearly see that in this direction, this is an acid. It donates that proton. This is a base. So it's an acid in the other direction. That's why it's called a conjugate acid, because it's the conjugate of that initial reaction direction. And for the other reaction as well, when we're identifying things, the base turns into the conjugate acid. So this is a conjugate acid, again, using the the big C notation, and then this is a conjugate base, C. And the Cl minus being a conjugate base should make sense, right? If it's a base, it's... Well, the other option is a conjugate acid, but how can it be an acid? It doesn't have a hydrogen on it, right? And the definition of an acid is a proton donator or a hydrogen donator, and it can't donate a hydrogen if it doesn't have one. It's a chloride all by itself, which is, it's kind of sad, but he's a little lonely, and he can't be an acid if he's lonely, because an acid gives away things. And how do you give away something if you're lonely? You don't have anything to give away. A little depressing, but yeah, it's basically the idea, and they're important to analyze because conjugate acids can react with other bases in solution if there's more than one base, which the reaction changes, and then everything's screwed up. But if you're not keeping track of what's screwed up, then you're gonna get some results in the lab that you're not expecting. So we're gonna need a new page for this. Well, I'll actually define this concept first, just because it's a little more straightforward. So something's a strong acid when it completely dissociates in solution. So if we think of HCl being in solution, I'll draw the little diagram here. So we have water, so this is my badly drawn flask, and we have some water in solution. We'll make that dark blue. So there's water. Make that clear. Water. H2O. So what happens here with HCl? I actually have to finish the drawing because that's not complete. There we go. Whatever. There we go. Now it's complete. So what happens with H2O? H2O is a polar molecule, right? So we have this water here. 2 hydrogens and lone pairs. This is a dipole moment, right? This is a polar bond right here. The OH bond is polar. There's a dipole moment pointing this way, dipole moment pointing this way. So the net dipole moment is going to be the sum of the two. I need to get better at drawing. Sum of the two, which is equal to tip to tail addition, and then the final dipole moment points, I'll make that green. The final dipole moment points like that. So it's a dipole moment going straight through the middle of the molecule. So it's a polar molecule, which means it will attract other polar molecules. And if we think about HCl, HCl is also polar. Right? We have HCl that has 3 lone pairs on it. That also has a dipole moment pointing right there. So the HCl, this is partially negative. I should have labeled that on the last diagram, but it doesn't matter too much. Partial negative, partial positive. So when you put the HCl in the water, the HCl and the water it's going to be attracted to each other, right? So if we think about this HCl molecule, here I'll draw it up here above the solution, right there. HCl it's surrounded by northern lone pairs because they're not really important for this demonstration. OH, H. These Cl's are going to be attracted to these hydrogens, right? Because there's a positive, partial negative, partial positive. So this Cl is going to be attracted. It's going to have attraction to that. It's going to have, and this hydrogen is going to have attraction to this oxygen because this is partial positive, partial negative, and opposites attract. Attraction there, attraction there. And that HCl bond is just weak enough that the water can actually rip it apart. The waters can actually rip it apart. And it'll turn out that part of the solution will become H3O plus because of this attraction right here. It becomes an oxygen with 3 hydrogens on it, which is a little weird to think about. This is called hydronium. That does not look like an O. I'm disappointed in my drawing capabilities tonight. Yeah, there we go. H. So this very much has a positive charge, and that comes from here. And the Cl doesn't bond with the H's because hydrogen can only form one bond, and the OH bond is actually pretty strong. It's not going to break that easily in the case of water. So the chlorine or the chloride will go towards the hydrogen, but it's not gonna do that. This is what's called to be a strong acid if this process happens completely. If all of the HCl gets ripped apart. So strong acid. I'll draw that in green just to give ourselves a little color variety. Strong acid. An acid fully dissociates. HCl in the presence of water forms H plus ions plus Cl minus. And the H plus in the H2O, it does form H3O plus. That is the more correct version. However, it's sort of ignored just because the water it does help in the reaction, but it's not a reactant or a product, just in the environment. So the H3O plus in this case is just, it's the same thing as H plus. And that triple line equal sign thing means equivalent to. Similarly, a strong base is something that fully dissociates with an OH. Strong base. Again, in the presence of water. So, for example, sodium hydroxide, strong base, that forms Na plus OH minus. Here, I'll draw that a little down there. And this is in the presence of water. So it's for the same reason. You can draw the diagrams of the individual water molecules and the NaOH and show it, but the big takeaway is that only some acids are strong and only some bases are strong, and you have to memorize them, which sucks. But eventually you'll use them so much that you'll know them. And I won't ask you the question again. Won't ask you like, is this a strong acid? It's a strong base. That's not an AP question. That's not a college level question. But you do have to use that knowledge and apply it to things like finding if a reaction will happen or not, or net ionic equations. So strong acids. There's a couple you have to memorize, and the reality is that whether an acid is strong or weak will differ by who you ask because it's measured with a number, and some people have different cutoffs for that number. For example, in organic chemistry, acetic acid's considered to be pretty strong acid, but it's definitely weak in terms of like general chemistry. So we're just gonna list the strong acids according to general standards. The great thing is that AP will rarely ask about those disputed ones because they know that they can't really control what teachers teach that well. So we have HCl, which means if your teacher has some of their own that they like to talk about, just follow theirs. So this is hydrochloric acid. This is nitric acid, HNO3. Then we have sulfuric acid, H2SO4. We have hydrobromic acid, HBr. Hydroiodic acid, HI. Chloric acid, HClO3. You don't have to memorize the names of these, but you will eventually. And perchloric acid, HCl4. And no, I'm not just pulling these out of my memory because I can't memorize. I have these written down on a paper right here. And then the strong bases. This is where a lot of the dispute is in the strong bases. But you do have to memorize these. Just because I don't have to memorize doesn't mean you shouldn't. The strong bases: lithium hydroxide, sodium hydroxide, potassium hydroxide. Some of these I do have memorized, but very minimally. Rubidium hydroxide, cesium hydroxide, calcium hydroxide, which has two OHs instead of one. Strontium hydroxide, and barium hydroxide. So if you notice something, these are all in the same column. The lithium, sodium, potassium, rubidium, cesium are all in the same column on the periodic table. So if you can memorize it like that, which is very useful. So memorize those, write them down, tattoo them on you. Don't tattoo them on you. So we're going to be looking at more in depth water's role in acid-base chemistry, because we already looked at it a little bit with the hydrochloric acid and how it sort of rips apart that bond, but we're going to look at it much more in depth. And this also includes a cool example of when an acid doesn't act like an acid. So we're going to be looking at the products between hydrochloric acid, hydrochloric acid, and acetic acid. Acetic acid. And you're wondering, these are both acids. Well, they're not going to react with each other. There's no proton donation because they both donate protons. So they donate, they're not going to accept it, right? But the reality is that hydrochloric acid is so much stronger than acetic acid that the acetic acid will act as a base with the hydrochloric acid. And it's also in equilibrium. So we're going to draw some Lewis structures we're going to draw some structures to talk about it. I'm not going to go through the steps of drawing the structure of acetic acid just because that's way too complicated to like reason out, and there's multiple ways to draw it almost. So, you know, we'll go with it. We'll draw the structure for hydrochloric acid. So this is hydrochloric acid, right? So there's two bonds, and then we count up the electrons, and we see that there's 3 lone pairs on hydrochloric acid. Which should be a little intuitive. But the structure for acetic acid is a little weirder. It's this structure. We have carbon down here. This carbon, we have a hydrogen, another hydrogen, another hydrogen. That's called a methyl group, CH3. Then we have another carbon right there. It's double bonded to an oxygen. Draw that more symmetric. There we go. And that oxygen has 2 lone pairs on it. And that has a bond with another oxygen, which has a bond with a hydrogen. That has 2 lone pairs. That OH is called an alcohol group. And this will react in the presence of water. The presence of water. Water is 2 lone pairs. Hydrogen, hydrogen. Why? That doesn't make sense, right? It's 2 acids reacting with one another. Why? Why would one act as a base? We're going to go through what water is actually doing the entire time, which I think is pretty cool. So we're going to start off, I'll draw the HCl with the hydrogen that actually does get donated. And this is step number 1. So step number 1 is the HCl is going to lose the hydrogen, which should be a little intuitive, and we're going to go into why or how. So we have an H bonded with the Cl. That Cl has 3 lone pairs. And then we have the water down here. Water with 2 lone pairs. So the whole idea is that the partial negative charge on the oxygen up here creates an attraction with the partial positive up here on the hydrogen. So it will actually move towards the hydrogen. And when that happens, we see that there's 2 bonds on hydrogen, which doesn't make sense. So the bond sort of dissociates, and what we have next is we have the same water. Now it's just sideways to make the drawing a little easier. And one of those bonding pairs is gonna go in bond with or create like a this is called an intermediate bond. It's gonna create an intermediate bond with the hydrogen there. Put that in blue. And then there's that Cl on the other end. And now hydrogen is stuck in a state where it sort of has like two bonds, which is not stable at all. So it's going to have to dissociate for somehow. And how it's going to do that is the hydrogen becomes bonded. This lone pair attaches to the chloride, which means that this new bond forms. And then, yeah, so now we have this leads to a hydronium ion with a lone pair. And this overall has a +1 charge. +1. So this also leads to a chloride ion, which I neglected to include, with 4 lone pairs. So that has a -1 charge. So that's the whole process, the physical process that's involved with the chloride leaving the hydrochloric acid. And now there's a sort of weird extra step that happens. So we have this ion right here. It's called the hydronium. We'll name it in purple. Just to add a little color, add a little eye appeal. And what happens next is acetic acid is going to attack that hydrogen. So again, I'm going to abbreviate this as CH3. This part is CH3, or rather H3C. You'll see why. It's the same thing. And then I'm also going to abbreviate this part as OH. The reason why it's H3C is because we're going to draw the bond. The bond isn't with the hydrogen, it's with the carbon. So second step, we have the hydroxide, or the hydronium. Rather, I'll draw it down here, just to make things a little more obvious. And that lone pair we were talking about earlier. So here's what happens. We have the acetic acid down here as well, which we now know is H3C bonded with a C, double bonded with an oxygen with 2 lone pairs on it. It's bonded with an OH. So we're just condensing the structure here. We're not drawing the bonds up there that are relevant or are irrelevant to the reaction. And the same kind of thing will happen here. The lone pair will attack the hydrogen, which will lead to a weird sort of structure again. With that intermediate again that we were talking about. So this forms an intermediate with the hydrogen, which is also forming an intermediate with the acetic acid. So it's a lone pair. Technically, this isn't linear. It would be bent, but I'm ignoring molecular geometry for now. So it wouldn't just be in a straight line like we're talking about. That intermediate bond wouldn't be parallel with this double bond. Or rather, draw that in red. Yeah, so the double bond there with the C, the CH3, then the OH. So there's a weird idea here now. We see the oxygen with way too many bonds than it should have. So again, it has to dissociate. And what happens is, let's see. Yeah, this lone pair, this bonding pair becomes a lone pair here again, which means that the hydrogen becomes attached to here, but we still have way too many bonds in that oxygen. So what happens is when this double pair or this double bond becomes a lone pair on the carbon. And I'm just going to ignore lone pairs in this final drawing. So this forms again the water plus, yeah, no, actually that does not go on the carbon. That lone pair swings to the oxygen. No, hold on, let me think about that. So that double bond, no, there's no way it swings there. So yeah, so it swings down here. My bad. Got myself a little confused there. And then we're gonna just ignore the lone pairs. HOH, water plus this weird ion. Comes H3C, C, then the OH here from before, the OH there, which doesn't really make too much sense. This also has a positive charge. So we see that the water participates in the reaction, but it spit right back out. So the idea here is that when we're adding up the reaction, when we're finding what was net, net ionic, if you watched that stream before, um, the water starts off in the beginning and is no longer there, or is there in the end. So it doesn't really matter in the overall reaction. So the overall reaction here is we have a Cl minus plus a CH3 C with two OHs on it. So I hope you can see that. That's just a CH3 right here bonded with a carbon, and then on that carbon is two oxygen or alcohols, two hydroxides. So that's that reaction, and that's how water participates in acid-base chemistry. It's what's taking the proton away from the acid and then giving the proton over to the base. So the whole Bronsted-Lowry definition is kind of misleading because it sort of sounds like the base is stealing the hydrogen away from the acid, but there's a middleman here. There's water, so it's more like a sort of Robin Hood situation where someone is stealing from the rich and giving to the poor. So the poor now have what the rich had, but in this case, the rich people are the acids. So the water steals the proton, and then the water takes the proton and gives it to the base. So that's water's role in acid-base chemistry. And that kind of thing can be generalized to a lot of reactions, which is good. It's nice. I'm looking at this now, and I think I screwed up somewhere with the reaction mechanism arrows, because the lone pairs weren't making sense to me in the middle of me doing it. That's why I was sort of spacing out a little bit. But the same general idea. The general idea holds. It's simply just the water is what's actually acting as the middleman that steals it, and it sort of almost makes sense. I'm gonna look up an example to talk about what I'm trying to say right now. Let's see, guanine. This is a base in DNA, and I'm going to be doing. Just let me draw this for a bit, and then I'll explain what the drawing means. If you don't get it right now, don't worry. That can be much better drawn. There we go. And then NH. There we go. And this has an NH2. And this has a double bond to the oxygen. There we go. This is guanine. If you don't know what it is, it's a common base, very common base. Without it, you wouldn't genetics wouldn't be a thing. This is a very important part of DNA. And the structure here for the notation here, for example, if we have this is also the same as a carbon with two hydrogens, double bond, carbon, one hydrogen, and then a carbon with three hydrogens. And basically, we draw the carbons as elbows. Every elbow in the structure is a carbon. Every second line is a double bond between two carbons, and we emit the hydrogens and the carbons whenever we can. So the idea here is that this base is really big. It's very large, and if you think of something like acetic acid, for example, we just drew that there, and I'll draw that with the notation that I just introduced. And seeing this, it may make sense why we use that notation because it's a lot simpler. So the idea here is it's guanine is a base. How is it going to attack? It's way too big to attack, right? Like if you're just thinking about it physically, like if you're thinking about like a plane trying to fly into a hole much bigger than it, it's going to break. It's not going to be able to do that. There's physical strain. So if you're thinking about it in the conventional way that the acid gives the proton to the base, or the more sinister way the base steals the proton from the acid, how is it going to go and attack the acid and do that? In this case, with like guanine, it can't. It's too big. However, if we're looking at the reaction, it's actually water attacking that hydrogen, and now it's something small attacking something much bigger, and there's a lot more room for error there because now it's something small attacking something big. It's like a small plane going through a big hole. Um, so the water there, because water is small and water is polar, can actually act as the intermediate in the reaction, which is very important for chemistry because if that weren't the case, then acid base wouldn't be a thing. So predicting products, I'm going to using a lot of acetic acid in these examples because it's a good example of a you know of a weak acid. So when we're thinking about an AOH, we're going to react an AOH with acetic acid. Gonna like color and do it down here. NaOH with acetic acid. And don't worry about memorizing just the formula for acetic acid. CH3COOH. You would have to memorize it for organic, but I mean, it'll just come to you. To be honest, it'll just get ingrained in your mind. What does this form? Well, the whole idea is that this is a double displacement reaction, right? The idea here is that this will form water because this may make it a little more obvious. We have the H and the OH here. This OH is a negative, and this H is a plus. So it's just a double displacement reaction. The H and the OH are gonna, they're not gonna switch places, but you'll see that'll form H2O or HOH. The negative there and the positive there are gonna react, plus sodium acetate, NaCH3COO. So it's more like the Na and the H are switching places. The positively charged parts of each thing are switching places, and we're gonna look at the net ionic equation here. Just because it's very important. So if we're looking at the net ionic equation, what we do know is that sodium hydroxide is going to fully dissociate. Just because it's a strong base, it's on that list of strong bases. So we can split it up in the reaction because it'll dissociate into sodium ions and hydroxide ions. But acetic acid is a weak acid, and the reason why it's a weak acid, it's the opposite of a strong acid. It won't fully dissociate. So we know that because it's not on the list of strong acids. If you're good at memorizing, determining something is weak or strong is as simple as is it on the list or not. It's not always going to be like that if you keep on going further with chemistry, but for now, that's how it is. So that acetic acid will not fully dissociate. So we'll just write that as it is. And the reason why, by the way, why the O isn't written as an O2 is because the O's are in different places. It's purely convention. You could write it O2 and it's just as right. And that'll form HOH, which is just water, plus, well, by solubility rules, anything with potassium, sodium, ammonium, or nitrate in it is going to fully dissociate. So this becomes Na plus acetate, CH3 COO minus. Right, because we have the Na plus and this CH3 COO minus combining to make one salt. So, if you notice something, this is sort of like an algebraic thing. The sodiums are gonna cancel. You have a sodium on both sides. Circle it and cross through it. Circle it and cross through it. And now the net ionic equation here is OH minus hydroxide plus acetic acid forming water plus acetate plus CH3 COO minus. And that's the net ionic equation. And this looks a little more familiar to the original Bronsted-Lowry definition of an acid base. We have an acid here, which is the acetic acid, plus the base, which is the OH minus, forming HB, H plus the base, which is HOH, which is water, plus the ion from the original acid, which is A minus, which is the acetate. It just so happens that the A in the acetate starts with A. Just so happens, which is a lucky occurrence. So it sort of happens very similarly with everything else. One thing to point out is that we're going to look at a strong acid, HCl, the classic HCl plus sodium hydroxide. If you like pop science or no science trivia, you'll know that this just forms water and table salt plus NaCl. And the whole idea here is that HCl is strong, so it fully dissociates into H plus Cl minus plus Na plus OH minus, forming water. Water is not soluble because what's defined as soluble is something dissociating in water, and water doesn't dissociate in water. If that happened, water wouldn't exist. NaCl is soluble because it has a sodium in it. We notice some canceling happens here. The chloride ions cancel. And the Na pluses cancel. And now we just have a simple hydrogen plus hydroxide forming water. And the idea here is that this is true for any strong acid reacting with any strong base. The net ionic equation will just be H plus OH minus plus H2O. The problem here is that you can't just say, oh yeah, if I put any amount of hydrochloric acid and any amount of sodium hydroxide in a flask, I'll only get water and table salt. NaCl is table salt, by the way, if you didn't know. That's a problem if you think that, because then you'll mix them and drink it. And both HCl and NaOH are very dangerous. In order for there to be no H plus or no HCl or no NaOH left, they'd have to be in equal molar amounts exactly. Because otherwise you have an excess reactant. Think back to limiting reactants in stoichiometry. If you put in, say, 2 moles of HCl and 1 mole of sodium hydroxide, you'll still have 1 excess mole of HCl, and that's really dangerous. Don't do that. So there would be HCl in the solution if you put in excess HCl, and there would be NaOH if you put in excess NaOH, by definition. Okay, so titration. We did a previous stream on titration. I think it was a stream before this one. But the whole idea here is that you have a burette and you have a long thin tube of something. I'll draw it out. Long thin tube. And there's a little dropper down there, and you have your thing that can actually, you turn it and it starts dripping. This is filled with something strong. Typically, it can be filled with something weak, but then you're kind of wasting product. And then you have a flask right here. Typically, this would be a strong acid like HCl or NaO. We'll say strong base. NaOH plus a weak acid. We'll say again it's acetic acid. I mean, I'm thinking drawing CH3, but that's not as right. CH3, COOH. And the idea here is that you could find out the molarity of either of them if you know the molarity of one, which is nice. Because what we have here is we have a titration curve. We can make a titration curve out of this. This is pH. This is volume of NaOH added. And the idea here is that it's acidic, but it's not a very strong acid. So it'll start at some pH, start at some low pH. It's acidic. And then as you add more and more and more, it'll become more basic. And what the curve will look like, it'll get a weird shape. It'll sort of start out increasing and then shoot up. And then this point right here, it's called the equivalent point, the equivalence point. And at this point, well, here, EQ point. I don't want to intersect any lines. There we go. And at this point, the moles of acid equal to moles of the base. And by definition, we can say that the molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base. Only at the equivalence point. And at this point, you could graph stuff, and you'd know the volume of the base, or the volume of the acid in this case, right? Because it's in a flask, and you could actually directly measure that. And you could measure the initial volume you have here. And then after adding in some stuff, it will, there'll be some change in volume. There'll be some change in volume delta V. That's a really nice delta. But at that point, you can measure that delta V, and that's how much volume of the acid was added. And from there, you can you will already know the molarity of the acetic acid. Popular thing would be to have some sodium acetate and just dump it in water. You know the mass of the sodium acetate by weighing it, and then from there you could find the moles of the sodium acetate, and you know the liters of water that you're dumping it into by measuring it, and then you use the moles per liter to find the molarities of the acid, or the molarities of the acid, the molarity of the acid. Yeah. And from there, you know the molarity of the acid. You know the volume of the acid by directly looking at your thing, and you know the volume of the base added. So in the equation, MAVA equals MVVB, MBVB. You know the molarity of the acid because you measured it earlier. You know the volume of the acid, and from the delta V, you know the volume of B. So you could solve for that. You could solve for the unknown. And the idea here is that you're not going to perfectly measure pH, right? You have to use software to get a curve that accurately. So what happens? You have a indicator in there, and the moment it's light pink, you measure it because light pink. There's some weird chemistry that happens, but when light pink tells you, or for in the case of phenolphthalein, which is the most accurate, or not the most accurate, but the most widely used indicator, phenolphthalein, I think that's abbreviated like that. Phenolphthalein, maybe. I don't know how to spell it. I'd be surprised if anyone did, really. That didn't do this for a profession. So at that point, you stop adding in the acid, and then you can measure stuff, which is very useful because then you could find the molarity of something without actually directly messing with it, which would be very, very useful. What else? Yeah, I think that's really it. We can do more practice on the titration stuff, but it's not really necessary. I mean, it's pretty much just applying equations. An important note is that if you had to balance the equation, like in this case, you don't have to balance it at all. But if you had to balance it and it was an acid-base reaction, like let's say it was 2A plus B forming C plus D, you'd have to do, let's say N is the acid, 2Na is equal to NB at the equivalence point. And the reason why is the equivalence point is measuring when something is completely neutralized. And if you think about it, in the case we have in the bottom right, the acetic acid is the limiting reactant because we can keep on adding sodium hydroxide as much as we want. The point that the acetic acid gets neutralized um, is just when all of it reacts to form something, um, to form a salt. Or in this case, it would form ions because the salt is a very strong electrolyte. So, um, yeah, it gets neutralized, and the indicator is reading when it gets neutralized. But when it gets neutralized in the example, in the reaction 2A plus B, um, you need 2 moles of the acid to neutralize 1 mole of the base, just stoichiometrically. Um, this should make intuitive sense. So you'd have to do 2 MAVA equals MVVB. That really trips up a lot of kids when they ignore the coefficient in the front of the acid because you're not really thinking about it. You're just kind of throwing a formula at something. Because to be honest, it's a waste of time to think about all this conceptual stuff when you're answering a multiple choice question or a free response question. Because you're just you know you're you're not going to be thinking about all this. Just throw a mathematical formula at something. You don't have the time to be thinking about all this. So there's a quick little note. Um, a lot of five was changing. And if you're watching the replay, then you already have access to this stuff. Come the next semester. So how five was changing is we're doing less streaming content and more one stream a week per subject, and um, basically the streamers are now going to make study guides and games and pre-recorded videos and stream every now and then. So the idea here is that I am going to probably be making study guides because I enjoy writing that stuff up. So if you have a specific question about stuff, put my Instagram up here in pink. So my Instagram is at jjeffries12. Yes, a little clear. You should see when you look that up the nicest picture that's ever been taken of me as my profile picture. Thanks to one of my friends, Susu. She's a very good photographer. I will never look that good in my life again. You can send me a DM there. It's my Instagram. If you have a question, I'd honestly love for you to send it to me and I could answer it if it's a homework question, and I also love to put it on a study guide. Just because it's really it's like I'm going to toot my horn as little as it possible I can here. It's hard to understand what people struggle with in chemistry when you're good at it. Um, so a lot of the concepts I'm teaching is sort of they were my hurdles when I was learning it. Um, for example, attacking the fundamentals was kind of my hurdle when I was learning it. But that's not the same for a lot of people. A lot of people just aren't that good at algebra in application to a science. So, um, but I don't have experience with that. Um, so, you know, when people send me those questions, I know, oh yeah, I put these on my study guide because even though I'm not struggling with them or I didn't struggle with them, a lot of people are. And if you want to send me something and think, no, not only I'm struggling with this, only I'm the idiot. Um, People are a lot more alike than people want to admit. Um, or we're a lot more like people. Like people are much more similar than humans generally like to admit. Um, so if you have a problem with something and other people probably struggle with it too. Um, because the reality of it is we're all pretty average people. That's what average means. So if you're struggling with something, someone else is probably also struggling with it too. Um, and again, that goes for anything with life, but I'm just talking chemistry here. It's not that deep. Um, so if you're struggling with something and you want to send me a question, but you're afraid you're gonna feel stupid about it, people are also probably struggling with it just as badly as you are. Just people don't want to admit it for the same reason you don't want to admit it. Um, and at that point, it also helps me better make study guides for people that suit people's needs and struggles more than anything else. So whenever you're watching this, I hope you learned something. Um, and take it easy. Have a good night or day or afternoon or morning, wherever it is.